All right, in this video, we are going to continue to do a ton of series multiple choice questions. This is part 3. I think there's going to be 8 parts. Part 1 and 2 obviously precede this. There should be a playlist or a link or whatever. You'll find them if you want them. All right, let's do some problems. So, what are all values of p for which the integral from 1 to infinity of 1 over x to the 2p diverges? All right, so this seems like what we're trying to do is, converges. I read that wrong. This seems like we're not doing series, but what I'm going to propose here is that we basically use like the reverse integral test. So the integral test tells us if the definite integral converges, the series converges. What I'm going to do is I'm going to say that if the series converges, then the integral converges. So I'm going to change this into a series problem and say that I'm really looking at the sum of 1 over n to the 2p, and I want to make this converge. So if a p series converges, the exponent is greater than 1. 2p greater than 1 means that p would have to be greater than 1/2, which means if I were going to use the integral test on that series, I would find that it converges, which means that the integral would converge. So my answer is p is greater than 1/2. Let's look at the next one. What are all values of x for which the sum of, so this is a little weird because the x is in the denominator, but the sum from 1 to infinity of n times 3 to the n over x converges. All right, so I look at this and in my mind, I'm like, I don't think this converges. I just think it diverges. So I'm going to do the work anyway because I don't actually know that, but that's my instinct on this problem. When I'm uncertain of what to do with the series, I basically just use the ratio test and hope that it works. So I'm going to set that up. Here, doing the n plus first term times the reciprocal of the nth term, which is how I always set it up. There's a lot of stuff that cancels here, so, this will end up. The n plus 1 and the n will cancel as we go to infinity. The 3 to the n and the 3 to the n on the top will cancel, so I'm left with 3 to the first. And then the x to the n will cancel with the x to the n in the denominator. So all that I'm left with here is 3 over the absolute value of x, which as n goes to infinity is just 3 over the absolute value of x. So I just need 3 over the absolute value of x to be less than 1, which means I need the absolute value of x to be greater than 3. If that is true, the series will converge. And that's really interesting. And that's one of the answer choices. I should have to test the endpoints. But I guess if I test the endpoints, I'm just going to get the sum of n, which will diverge. So the answer here is D. My instinct was that this diverged. I was definitely wrong. So let's take a look at another one. That's why you do the work. Which of the following is conditionally convergent? So we need to remember that conditionally convergent means it converges when it alternates, and it does not converge when you take the absolute value. So we have to worry about whether or not this absolutely converges first. Let's see. So for the first one, we've done this comparison before. Sine is between -1 and 1, so the absolute value of sine is between 0 and 1. So sine of n over n squared is less than or equal to 1 over n squared. And then 1 over n squared converges, which means that this series converges absolutely and therefore is not conditionally convergent. All right, we'll look at the next one. First up, I'm just going to cross out the 17. I don't know why there are 17s in every part of this problem, but there are. So I'm crossing that out. I'm just going to look at this series, -1 to the n plus 1, and then n over n over root n is radical n. I thought I had messed that up, but I didn't. N divided by radical n is n to the 1/2. And then if we take the limit to infinity, we do not get 0. So this will actually diverge by the nth term test, even while it alternates. So it's not conditionally convergent. It doesn't converge at all. For the next one, again, we're canceling out the 17. I'm going to do the same thing. I'm going to look at the absolute value, right? Because that's the important thing. So on the previous one, it didn't matter because the nth term test just told us that it diverged. Here, I'm getting 1 over the square root of n. That might converge. So I'm going to look at the absolute value of the terms. I get 1 over the square root of n, but that's a p series. P is 1/2, less than 1, so that diverges. So then I have to look at the original series, n, -1 to the n plus 1 over radical n. That converges by the alternating series test, right? It alternates, the terms decrease in magnitude, and the limit of the nth term is 0. So it converges by the alternating series test, converges when it alternates, diverges when you take the absolute value. That by definition is conditionally convergent. So that is our answer. For part D, this is geometric. And so you may never have like framed it this way in your mind, but all geometric series that converge are absolutely convergent. The geometric series test, where you look at the absolute value of r, is basically a test for absolute convergence. So a convergent geometric series is going to converge absolutely. It will not converge conditionally. All right, next up, 22. For what values of p is the series -1 to the n times n over n to the p plus 2 conditionally convergent? All right, so step one is ignore that plus 2. If you do enough of these, you will get used to that. It feels very dicey at first. But now that we've ignored that, I'm looking at this and I'm thinking this is like kind of -1 to the n and then like times a p series. So a p series, whether you have an alternating p series or just an absolute value p series, if it converges, it will converge absolutely, right? Because -1 to the n over n to the fifth, the absolute value is just 1 over n to the fifth converges. So if you have a convergent alternating p series, it will definitely converge absolutely. So if we end up with a convergent p series, it will converge absolutely. That's kind of a problem. So let's rewrite this thing so it's a little easier to deal with. Keeping in mind I've gotten rid of the plus 2 because it's just there to mess you up. So we got rid of that. We have -1 to the times -1 to the n times n over n to the p. We do the thing where we bring the n to the denominator, not to the numerator. So I have -1 to the n over n to the p minus 1. I need this when I take the absolute value to diverge. So I actually need p minus 1 to be in between 0 and 1, because that would make the exponent of n something between 0 and 1, which would give me a divergent p series. So if I solve this, I get 1 to 2, including 2. So I feel like there's a weak explanation of this, but what I'm basically saying is, say p is equal to 3, right? Then you have -1 to the n over n squared. 1 over n squared converges, so that converges absolutely. If you had 1 over n to the, I don't know, 8th or something, -1 to the n over n to the 8th, absolute value is 1 over n to the 8th, that converges. So we need to force the exponent of n to be between 0 and 1 when all is said and done, so that we diverge with absolute value and then converge with alternating. So that's why I'm going with this as my answer. All right, so you might need to rewatch that one because I feel like I didn't explain it very well. 23, which of the following statements is true about the series -1 to the n over the cube root of n? All right, so step one will be to take the absolute value and see what's happening. So I've done that. I get 1 over n to the 1/3. 1 over n to the 1/3 is a p series. P is 1/3, which is less than 1. That diverges. So as soon as that diverges, we know for a fact this series, the original series, does not converge absolutely, because if the absolute value diverges, then that's off the table. So now the question is, does the original series converge the way that it's written? In which case, it will be conditionally convergent. So this is an alternating series, and it does converge. The rules for that are that it alternates, the magnitude of the terms decrease, right? So the terms decrease in magnitude, and they need to have a limit of 0. If those three things are true, then the series converges by the alternating series test. So converges when alternating, diverges with absolute value. This is conditionally convergent. So the series A, I think A is the answer, converges conditionally. All right, let's take a look at another one. Consider the series. Oh, that's like plural, the series. From 1 to infinity, -1 to the n over the cube root of n. That's literally the problem that we just did. We know that that converges conditionally. And from 1 to infinity, -1 to the n over n cubed. We actually already talked about this too, right? We said that if you get an alternating p series, which isn't really a thing that people talk about, but like I guess it's an alternating p series. If the absolute value converges, like if p is greater than 1, a p series is always going to converge, whether it alternates or not. So we kind of know the answer to this, but let's do it anyway. All right, so this is literally the problem we just did. We already know that this converges conditionally, so I'm not going to do the work again, just like go back and look at that again. And then we need to look at this one. So we're going to see if it converges absolutely. But we talked about it. It definitely converges absolutely because the absolute value of the terms gives us 1 over n cubed. That's a p-series where p is 3, which is greater than 1. So that converges. Therefore, the series converges absolutely. So the second one converges absolutely. The first one converges conditionally. The answer is D. And let's take a look at another problem. This is actually a really neat question. I'd never done a question like this before, and I'm glad that I ran into it. So consider the series from 0 to infinity, -1 to the n over 2n plus 1. Now, it's nice that they gave us a couple of terms because we actually need those to kind of like figure this out. So it's 1 minus 1/3 plus 1/5 minus, minus 1/7 plus 1/9, like, etc. Which of the following statements is true? So I was just expecting it to be like converges, conditionally, whatever. It's not. It's that the series converges and the sum is between 1/3 and 2/3. The series converges and the sum is between 2/3 and 1. The series converges and the sum is greater than 1. The series diverges. So this is really interesting. I know for a fact that this is a convergent alternating series because we can use the alternating series test if we wanted to. But the most relevant thing here is that the error is at most the first term left off. So what does that mean? Well, that means if we can say that the answer, that series is approximately 1, but then we're at most wrong by 1/3. But it's kind of important because we're subtracting 1/3 that actually the series is approximately 1, but it's definitely less than 1 because we would subtract 1/3 to get our next estimate. And then we could say that the series is approximately 1 minus 1/3 with an error of 1/5, but we're adding that. So it's really 1 minus 1/3, but more because we would have to add 1/5 to get our next estimate. So if you think would my next estimate be bigger or smaller, you can work this out. So I'm going to say that the first term is 1, and then the first error is 1/3. So my sum is approximately 1, but since I'm subtracting 1/3, it's actually less. I know that I'm approximating it with 1, but the sum is actually less, which means that the sum itself is less than 1. I can do that again. I'm going to use the first two terms and say that the sum is approximately 1 minus 1/3, which is 2/3. And then the error is 1/5, which means my next estimate, I would have to add 1/5. So I'm going to say that the sum is approximately 1 minus 1/3, so 2/3. But I know that it's actually more than that because I would have to add 1/5 to get my next thing, and then I'll never subtract enough to get less than that again. So the sum that I'm originally using is bigger than 2/3. So it's less than 1 and bigger than 2/3. So the sum is between 2/3 and 1. This is a great question. I really liked this. I plan to put this on some quiz or test later in my teaching career at some point. All right, new problem. This one is the thing of nightmares, kind of. I don't know that this seems like a lot to be on an AP exam. I don't really know where I got the question from, but it seems like a lot going on. The alternating series test can be used to show the convergence for which of the following series? Alternating series test is the terms alternate, they decrease in magnitude, and they have a limit of 0. So that's what we need to think about. Alternate, limit, decrease in magnitude, limit of 0. So the first one is like a slam dunk, right? It's just -1 to the n plus 1 over n squared. That the terms definitely alternate. They definitely decrease in magnitude. They definitely have a limit of 0. Definitely converges by the alternating series test. So that's a yes. All right, the next one is annoying because it's -1 to the n plus 1 sine of n over n squared. Well, sine of n isn't necessarily consistent in whether or not it's positive or negative. So I'm thinking this would be no, but I'm going to do the work because of the video. On the AP exam, I would probably just say nope and move on and hope that I was right. I mean, I'm pretty sure that I'm right. We need to figure out if -1 to the n plus 1 times sine of n is truly alternating. Are we really going positive, negative, positive, negative? We can do that because we kind of know, we definitely know the unit circle, and we kind of know where to put things, right? So pi is 3.14, so divide by 2 is 1.57, and then I just added them to get 4.71. I can never remember that one. Okay, so what are we going to do? Well, here goes. I'm going to make a little table here that has n and then -1 to the n plus 1 times sine of n, just figure out signs, right? So when n is 1, I get the sine of 1 definitely falls because 1 is between 0 and 1.57, so I'm in the first quadrant. In the first quadrant, sine is positive, and -1 to the 1 plus 1 is -1 squared, which is positive, so I get a positive and a positive, which means overall positive. And I'm going to keep doing this. All right, for 2. So 2 is going to put me in the second quadrant because 2 is between 1.57 and 3.14. That's the key here. So you can see like sine of 3 is going to fall in that quadrant as well. But whatever. All right, so when n is 2, I get -1 to the third, which is negative, and then the positive for sine of 2, that's less than 0. So far we have a positive, then a negative. We're good. So for 3, we're still in the second quadrant. So we have -1 to the fourth, which is positive, times a positive is positive. So we're still alternating. 4 is going to put us in the third quadrant. So now we get, -1 to the fifth is negative, and then sine is negative, so we get a positive, so we are not alternating anymore. That's it, we're done. This is not an alternating series. The answer is no, which is what my gut was telling me to begin with and what I would have done on the exam. But on the video, I think it's important to show the work in case you've never seen or thought about this kind of thing. So there you go, that's a no. All right, good. Now we move on to the third one, which, I don't know, I just hope doesn't, I guess. So I'm going to say, my initial thought is, and then, I don't know, let's look at these terms, right? So they wrote them out for us. I definitely know that radical 2 plus 1 is bigger than radical 2 minus 1. Like, that's a given. So now, if I flip them, I also flip the inequality. So 1 over radical 2 plus 1 is actually less than 1 over radical 2 minus 1. And I feel like I found a loophole because that's not decreasing. That term increased. So we can't use the alternating series test on this. It does not meet the requirements. So those terms are not decreasing in magnitude. So the answer is no. I feel like that's a loophole and not maybe how you're supposed to do it. Maybe it is how you're supposed to do it, though. I'm not sure on this particular problem. But anyway, that's enough to answer the question. So only the first one can you use the alternating series test on. All right, let's move on. This problem's terrible. So we're given the graph of g, and it's crazy. Let f be the function defined by f of x equals 2 plus cosine of x over x squared. Okay, the derivative of f is given by that thing. The graph of the function g defined by g of x equals x squared sine x. It doesn't really matter, that's just g of x. And we have the graph, is shown above. Let b sub n equal f of n. So b sub n is just that, right? It's 2 plus cosine of n over n squared for all integers n greater than or equal to 1. And then, okay, so those are the same, which is relevant, and they probably should have said that. Or just, why couldn't they just write f prime as negative g over x to the fourth? That would have, like, simplified this by a lot. So that means that, I'm going to write it. F prime is negative g over x to the fourth. All right, so which of the following is true? The series converges by the alternating series test. The alternating series test cannot be used because the series is not alternating. The test cannot be used to determine convergence because the limit is not 0. And then the alternating series test cannot be used because the terms are not decreasing. Okay. Alternating, there's a lot going on. Okay. So, I mean, well, I don't know. Look at the graph of G, right? So the graph of G is wildly swinging between positives and negatives. And f prime is the negative of G over x to the fourth. X to the fourth is always positive. So really, negative g of x is just this graph, but reflected over the x-axis. So f prime is swinging wildly between positives and negatives. And since f prime is swinging wildly between positives and negatives, I would say that that definitely has sign changes. And that means that the terms are not decreasing in magnitude. And so I'm going to say that the answer is D. I do not like this question, but that doesn't matter, right? Because if you're asked to answer it, you got to answer it. All right, so that was 9 more. Parts 1 and 2 are in the playlist. The following parts presumably exist. I hope you found this helpful, and good luck.